Okay, so it's time for the next talk by Matteo Marescotti.
Thank you. Yeah. Hi everyone, I'm Matteo, and today I'll talk about how we use static analysis data at WhatsApp to provide Infer with additional information to perform better and in some ways to supercharge Infer. So first of all, WhatsApp is one of the most used messaging application in the world. It's used every day by around 2 billion people, so that's a lot of people, and so these people use WhatsApp to exchange messages, and that means exchange a lot of data. And just to give a sense of how much data they exchange, this is the number of messages they exchange every day is around 100 billion. Like, it's actually a lower bound, so it's even more. And the data starts from clients, so phones, and end up in clients. But over the way, and it passes through a server, right? But the server is not a single entity. It's actually a set of microservices, so there are a lot of them. And they are divided in regions, so there are several around the world. And all of them exchange also data. So keeping track of where data goes, and also within the server is quite complicated, not only from clients to server, but also within the server. And what our team tries to answer is this question, like, no sensitive data flows exist from any source to any sink for a given set of sources and sinks that are provided as specifications. And I want to present my team, so the work I'll be presenting here has been made possible by all these people, and we are the Privacy Cat, where CAT stands for Code Analysis Tool, unfortunately, but yeah, the logo shows instead a cat. It's cooler. So I said that we try to answer this problem, to face this problem with both static and dynamic analysis, and we do it with several tools, but the only static analysis tool we use for this purpose is Infer, and more specifically the Erlang integration. Yeah, just told. Oh, no, this is a problem. Okay. Yeah, sorry. Thank you. It's a mess.
Do you want to properly wipe it? You know this.
I think it's okay. Yeah.
You think so?
Yeah. Yeah, I think it's okay.
There's a bit of water between the keyboards.
Yeah, but as long as it doesn't die, I don't want to touch the buttons.
This is here.
Okay, yeah.
For you, and then we can fix the rest of
Sorry for the mess, yeah, okay. So I said that we have several tools to answer this question, and we use Infer. Yeah, this is the Erlang integration. So Erlang is one of the several languages that Infer understands, and it's yeah, it can check for reliability issues and also data flow properties. This is what we use it for. And we use several dynamic analysis systems instead. If one of them is Fausta. This is the one we use as a source of input for this integration between static and dynamic. So this is the one I will cover more, but we have several others. For example, we have end-to-end tests that cover specific cases of interaction between client and server, and also Sapiens that simulates real touches in the interface and monitors what's happening in the clients and in the server. Fausta instead performs traffic generation, so it instantiates real packets of data that they look like this. They're called stanzas, and they and it creates a sandbox of the server, and it starts to move around these stanzas from clients, fake clients to servers, like in this sandbox. And the way these stanzas are generated is from a specification that is originally intended to be used on the server side for validation. But since they contain also the expected type of data, this is used by Fausta to create legit information. Like, for example, there the spec says that it expects an IP with port, so Fausta knows how to, Fausta knows that there should be an IP, so it creates an IP and sends the stanza. So the server does not reject this stanza and performs as if it was running in prod, basically. Instead, for static analysis, and we do data flow analysis using Tuple. Tuple is an engine inside Infer to do this data flow analysis, and the property has a form of a finite state automaton, like the one on the bottom. It is capable of, like this finite state automaton represents a possible data flow from a source, a function called source, to a function called sink. And Infer knows how to move in this finite state automaton based on the function being called. For example, when there is a function called source, the return argument is stored in a variable called dirty that is carried over with the finite state automaton and in a new state. And then there is this loop, non-deterministic loop for all the other statements that are not relevant. And when there is a call to sync and the first argument happened to be dirty registered before, then the automaton goes to the error state, and the flow from start to error inside Infer is the issue, so is the real issue that is reported at the end. So we have a problem here. The first problem is that if there is a complex function in the middle, then Infer is not capable of following through and transition to the error state, because complex functions are treated as by Infer as a non-deterministic function that return a non-deterministic value. So what happens in reality is that Infer don't know how to do, like, don't realize that argument is actually dirty, so it doesn't take this this transition. So the error is actually missed. And the second problem is, this is a slide on demand, like similar to the one Jules showed us this morning. So it's very similar. We have this function bed that calls another function complex. And what happens is that Infer tries to compute the summary of complex, but because of its name, it's not possible to do. So it fails. And this is also used to compute the summary of bed. So if Infer fails to compute the summary of this function complex, then also doesn't produce a summary of bed. So there is this chain reaction that. So if there are several complex functions that have a lot of dependencies, we end up with limited coverage. Like by coverage, I mean summary functions with some summaries. And this is why initially we created the Erlang models. And the Erlang models are ways to provide additional data to Infer, like additional on top of the source code, to substitute some of the functions with input-output pairs. It works well, and it is Erlang specific because Erlang functions are pure. So there is no state, and there is no global variables. It's some things make Erlang a bit better for this work. So you just provide input-output pairs. Once you know the arguments, you know the return values, and that's all you need. So yeah, the structures and input-output pairs can be provided in JSON or in SQLite format. So these are, I'm also providing this slide, although the information is available in the manual, the Infer manual. This is how they are defined in JSON. Basically, there is a list of arguments. It is a list of Erlang values as for the argument, and the return is one only Erlang value. And the Erlang value can be an atom, and then the name, an integer, its value as a string, a list, so it's like a recursive type, like a list of Erlang values, or a tuple is similar to a list and treated similarly. And finally, there is this function value null that is used to represent non-deterministic values. So when null is provided, basically it always matches, and everything matches. So if it returns null, it means that it's non-deterministic, basically. Yes, this is important. Functions for which a model is provided are not analyzed. That means are completely skipped. Infer doesn't read the source code for these. It just relies on these input-output pairs, and during the search, if there is a matching between what is passed, then the respective return value is used. And if it collides with some assertion, then it is an error. Yeah. Coming back to what Fausta does on the dynamic side, yeah, Fausta is a complicated framework. I'm not going to explain that picture. This is just to prove that it's complicated. It has a lot of squares. So but what it does, yes, it instantiates this sandbox, and it creates clients, and it makes clients connected with the server and exchange information. The interesting piece of this slide is the component down below. This is a built-in module of Erlang called DBG, and is the trace-based facility. It can be plugged into any Erlang system running. And what it does, it takes as input a list of Erlang functions, and it produces as output the traces that are arguments and return values for each call that happened during the execution. So this happened in real time, and it writes them real time in like some Erlang format on some file. Yes, so basically by plugging in the text-based facility to Fausta, we are able in real time to get the arguments and return values of a list of functions while the server is running and while this information flows from client to server. So the missing piece to basically connect dynamic and static is the trace to model, right? We have the traces, and we would like to have them as Erlang models, so we can plug them in as we do, right? And this is the missing piece of this connection, and is this module trace to model. And yeah, it takes this GDB traces written that have a format that is Erlang specific, and transforms them to JSON, basically, or to SQLite, depending on how many they are. The SQLite is easier because they can be indexed by name, and it's faster for Infer to fetch them while doing the analysis. This is the interesting part is that, like, we use Fausta, and I will show experimental result we using Fausta, but any Erlang system can be plugged into DBG. So also tests, Sapiens, everything, like in general the server and any kind of dynamic analysis can be used. So it's not Fausta specific. So yeah, this is just how the translation is done. These are Erlang types, and the respective Erlang model JSON produced. So atoms just become atom. Yeah, same for integer, list, and any type that is not in this list, like for example records. Yeah, so that there is some missing types that return null. So it means it's non-deterministic, and everything can, all the values will match. So this slide instead is an end-to-end example of how the big picture about everything. So we have this code with a simple function that increments an integer provided as input, and a complex function that transforms the input into string. This is performed by integer to list, since in Erlang strings are represented as list of characters. And yeah, suppose that this function is complex and Infer fails to analyze. When we call complex of 42 with GDB, the tracer, we basically get the input and output of both inc and complex. So, and it look like this. For the function inc, we get arguments 42 and return 43. And for the function complex, we get as input 42 and return a list consisting of the characters 4 and 3. Yeah, so 52 and 51. After trace to model consumes these traces, this basically there is a list of only 2 because the function calls only once, but if there are more other calls, all of them will be recorded and will produce one of these JSON items on the list, and each of them represent a single specific call. So we also implemented abstraction because, as can be seen from here, every model is a specific input-output pair. And after running the server for a while, we get millions of these. And there are too many for Infer to consider one by one. And we implemented some abstraction. And it's a very initial implementation of abstraction. So basically, we keep a list of what we are interested in. And for all the rest, we just say it's non-deterministic. So for atoms, we keep a list of atoms that we're interested in. And if in the input-output pair, there is any of them, then we keep the precise, the concrete value. So for example, true, false, there are atoms that appear very often in the code. If there are other atoms that are constructed on the run, for example, during handling of a call that contains specific identifiers that we are not interested in, like they're very specific, then we just treat them as non-deterministic. For integer, only 0 and 1. And for list and tuples, we keep only the first 3 elements. And if there are more elements, we just append a non-deterministic variable at the end. This helped reduce the number of input-output pairs a lot, and allowed also Infer to consider more. Yeah, I have also this slide to show this. Yeah. So the square box represents all the real program behaviors, and the light green circle the behaviors that Infer explores. Since it does under approximation, this is like the way under approximation does. It just considers a subset of all the real program behaviors. So dynamic behaviors provided by dynamic run instead are also a subset of real program behaviors, because by definition they're just concrete data points of input-output pairs. And yeah, this is an over-approximation. But by doing extraction, we mess it a little bit up, right? We provide behaviors that, of course, are a superset of the real behaviors, because we start from them. So we don't exclude any of them. But we can also go and in over-approximation side. So we do this kind of, and we lose soundness. But it's not a problem for us, because we are looking for bugs, and it's okay as long as we don't find too many issues, but this is not happening yet. Yeah, and this is the last slide, is about some experimental results. So I sampled 25 runs that are happening in CI every hour. And for them, I ran specific statistics over like all these specific runs. And like on average, Infer covers around 140,000 functions. So it means that it is capable of provide summaries for this amount of functions. And this is the baseline. This is what is basically 0. And the blue bar is the amount of functions that are provided dynamic summaries. So this input-output pairs. And as a result of providing the blue bars, we get the green bars that are additional functions that can be summarized by Infer only because we provided the blue dynamic models. Right, yeah. And this is the improvement is 2.1 times. So we get 2.1 more times more functions covered. So for which a function can be provided than the dynamic models that we get. So it's quite. This is the interesting result, yeah. So in the end, we get a 3-4% more functions covered, like from the base, from 140,000. But it's surprisingly that giving this dynamic models allowed also Infer to explore 2.1 times the functions, yeah. Yeah, introducing one new summary can potentially result in multiple new summaries. This is what happens, yeah. And we also have an increase in detected bugs on 66% on the runs. Yeah, this is also a positive result. And yeah, this concludes my presentation. Yeah.
Thank you for the talk. I wonder what sources and sinks do you actually use in your trace analysis? Can you tell?
Yes. We use custom sources and sinks, and we track data that we are interested in for privacy purposes. So privacy-sensitive data sources, and sinks are logs in general that log data. And yeah, these are the sources and sinks, but they are manually provided, yes.
Gotcha. And how many of those sources and sinks do you have?
Sources, I think there are not many. There are functions that there are not many, I guess around tens. And for sinks, there are way more, because there can be all the logs places within WhatsApp. Yeah.
Thank you.
Thanks. I don't know if I missed that. How do you choose the functions that you will pass on to Fausta to get dynamic traces?
Yeah, this is something that I might have forgotten to say. Yeah. So we do an initial Infer run. And from the initial Infer run, we list all the functions that have 0 summaries, so that are not covered. So this is the list of functions that we pass to the tracer for being monitored during the execution. And not all of them end up having traces though. So.
And do you repeat that process?
Every hour, yeah.
I mean, as in with the existing, not with the initial run, but after you provide the first wave, let's say, of dynamically defined summaries,
yes.
Do you then redo this and see which other ones could you, yeah?
We don't do it, but we wrote a paper, it's under review, that provides an algorithm to do it iteratively until a fixed point is reached. And this is, yeah, we didn't test it, but it might be, yes, that providing other dynamic models with this Infer run can help add even more, yeah.
Yeah, and sort of conversely, so you start from the functions with no summaries, but some of them have no summaries because a callee didn't have any summary.
Yeah.
So do you exclude those, or you just take all of them? If you see what I mean.
Yeah, but in the original Infer run, you're talking about the original Infer
Yes,
run.
when you gather the list of functions you want to monitor.
Yeah, we give all of them to the trace, yeah. Yeah.
So if I understand well, there is a risk of false positive. And did you any experiment that did you have any experiment that tried to understand if there was any in practice an increase of false positive with your approach?
No, because every time we find an issue, especially with tuple, we check in if the prod systems have traces of that particular data being logged for real. So we do like a prod matching of an issue. So this is something that prevents like this unsoundness to reach the developers and to let people waste time on false positives. And it works quite well, and there are no cases where really a false positive reached a developer, bother a developer, and yeah. So especially for this prod matching, but yeah, there can be cases, and but they're under control. This is basically, yeah.
And do you have any plan to complexify a bit the summaries that you generate? So you show us the patterns that you allow in your generated summaries, but you think you generate a real control flow graph with disjuncts. I mean, with branching. Would you be interested in generating more complex summaries at what you currently do? Is there
So it is extensible, like the language for providing input-output pairs is extensible, and for now it only allows to provide this like input-output pairs as concrete values. I guess if we want something more complicated, then we can just have like the some models provided in SEAL. So so I think it would be better also because it would be compiled, so it would be like an OCaml code, and it would be also faster to evaluate during the analysis, right? Because these also eventually become SEAL models, but they're very simple, right? Just input and output.
Can you share an example of a true positive bug that you found? So something where something leaked from a source to a sink?
Yeah, we don't have it like. No, I don't have anything in the slide, but like in general, so the true positive look exactly the same as an Infer run without the dynamic data. It's just that without it, it wasn't able to produce it. Yeah. So.
Thanks.
Yeah, I think you might have just explained this, but so the dynamic behaviors are input-output pairs. And that gets analyzed by Infer by essentially the equivalent of generating code for that function that says if input equals this, return this, and then Infer analyzes that code, and that's how it introduces its own abstractions to compute its stylus summary. Okay.
Yeah, the code is ignored. The real code of the function is ignored, and instead this input-output pair is used. But the input-output pair is exactly as you said. It's like a function with some inputs and then a lot of conditions. If the input matches this, then this is the output. Yeah.
Okay, I think we will stop here. Thank you very much.